everybody. This is Danica Oman with CSAFE at Iowa State University, and thank you very much for joining me for part 2 of my webinar on covering the basic concepts surrounding the weight and strength of evidence. So some of the work that I'm going to talk about today is some of the stuff that I worked on as part of my PhD dissertation, and that was funded partially by an NIJ grant led by Dr. Saunders and Dr. Newman at SDSU. And some of the examples that I'll talk about today were some things that projects I started working on as a visiting scientist with the FBI. So I'd also like to acknowledge Joanne Buscalia, who was my mentor for that program. So just a couple of disclaimers here, because this was funded by NIJ and partially by the Visiting Scientist Program. Anything I say today is, of course, reflective of me and my views and doesn't represent the US government in any way, shape, or form. Just me. So, as just kind of a brief reminder, this is the second part of a two-part webinar. So in part 1, we talked about just kind of a brief introduction to what the value of evidence was, and then gave a timeline of events that led us up to where we are today with some of the research that we've been doing on the value of evidence. So today we're going to talk about some recent developments that we've made towards trying to quantify what the value of evidence is, and then talk about some controversies that have arisen as we've been going along this path that we've been following. So let's go ahead and get started with that. So you'll remember last time we talked about there being kind of this hierarchy of propositions that we could address. And so today's developments are going to focus on just one particular level of that hierarchy. So we're going to focus on the source level hierarchy. And so some of the things that I've been doing for my dissertation have been looking at two common questions that typically arise in value of evidence type problems. And so I call those the common source and the specific source frameworks. So we'll talk a little bit about what those are and what that looks like. And so part of what that looks like is that we have been explicitly incorporating the evidence or the data from the relevant background population into everything that we've been doing, so into this common source and specific source framework. And so if you'd like more details about that, I recently published a paper with Chris Saunders in Law, Probability, and Risk, so you're welcome to check that out for more details. And then for the second part of this, we're going to talk about some ways that we can come up with statistically rigorous value of evidence approximations. So we'll talk about the relationship between the Bayes factor and the likelihood ratio, as well as what I call the Bernstein-von Mises approximation to the Bayes factor and the Neyman-Pearson approximation to the likelihood ratio, and talk a little bit about why I think those are important. So let's start out with an example that's going to motivate these two different frameworks. So let's imagine that there has been this crime. So there are two different crime scenes in which some improvised explosive devices or IEDs have been found. So one question that you might ask yourself is, if there are these two different IEDs that have gone off at two different crime scenes, and let's say that the people analyzing this crime scene have found some copper wire, you might ask yourself, can the copper wire from these two different IEDs be attributed to the same source? Kind of implying, did the same person make these two different IEDs? Okay, so this might help you figure out whether you're looking for one person or whether you're looking for multiple people. So let's say you're looking for one person, you find a suspect, you go to that suspect's garage, you find some copper wire in their garage, and you want to figure out, well, was the copper wire that made the IED, did that actually come from this suspect's garage? So can we figure out whether or not the copper wire was indistinguishable from the stuff that we found with the suspect? So these are the two different scenarios that we're going to be looking at today. So at different parts of this scenario, you might ask yourself two different questions. So the first question we asked ourselves was, could the copper wire samples found at the crime scene come from the two different crime scenes come from the same coil, or can the copper wire found at the one crime scene be attributed to the wire we found with the suspect? Okay, so these are the two different questions that we're going to be looking at today. And there's a really subtle difference here between the two questions. They look very similar, they sound very similar in their nature, but the real subtle difference between these two questions is what we consider with the sources. So for the first question, where we're trying to figure out whether or not the copper wire from the one crime scene can be linked back to the suspect, well, that source related to the wire coil that we found with the suspect, we consider that to be fixed. That's going to be different from that second question where we're trying to determine whether or not the two different bombs can essentially be linked to each other through the copper wire, and that at that point in the scenario, we don't have a specific person in mind. So we don't have a specific source of wire that we're looking at. So we just want to figure out whether or not they share a common, but we don't know what the source is. So a common but unknown source in this case. Okay, so let's start off with this first question, and this is what I call the identification of specific source problem. So in this scenario, the evidence or the data that we have to deal with can be split up into three different pieces. So the first piece I call E sub S for specific source, and that's going to be the control samples that we have taken from the wire coil in the suspect's garage. So that's the specific source. And I denote that there's N sub S of those samples. The next subset of the evidence is what I call E sub A, and that's for the alternative source. So this would be what people often call the background population or the alternative source population. So you've taken some samples that you would consider relevant, and there's going to be N sub A sources from which you've taken samples. So that's E sub A. And then finally, we have E sub U for unknown source. That's the copper wire that we found at the crime scene, and we're trying to figure out where the source came from. Okay, so those are the recovered samples from the crime scene. Okay, so in relation to this question that we ask ourselves, we can define these two forensic hypotheses, or these are our source level propositions for this specific source example. So the first one is related to what we call the prosecution proposition. So that's saying that basically the recovered and the control samples both came from this fixed specific source. So that's like saying the wire coil in the suspect's garage is where the wire came from to make the bomb. What the defense proposition is saying is that that didn't happen, that the recovered samples from the crime scene came from some other source in the alternative source population. Okay, so let's take a look at this a little bit closer. And so really what we have here are a couple of different models for how the unknown source evidence could have come about. Okay, so first of all, let's take a look at how the alternative source population evidence E sub A has been generated. So we have this population of alternative sources, and that can be described by this parameter that we call theta A. Okay, so what we do is from this population of alternative sources, we sample N sub A sources. And then from each one of those sources, we sample some number of samples from each one of those sources. And that's what E sub A consists of. And then let's take a look at, well, what happens for our specific source, this other piece of evidence, E sub S. So you're looking at this population associated with the specific source, and we denote the parameter that characterizes that population as theta S for specific source. And for that specific source evidence, you just take some samples from that specific source population, and we call those E sub S. Now, really what we're trying to figure out is where E sub U came from. So did E sub U come from sampling a new source from the alternative source population and then taking some samples from that source? And that's what would happen under the defense proposition, so that's under the M sub D. Or did this come about by taking some more samples from the specific source population where E sub s came from. And that's what the prosecution proposition is trying to tell us. So one thing I want to note here is that in the Bayesian scenario, so let's say we're going to try and find a Bayes factor for this case, we're going to need some priors. So we're going to put some prior distributions over that space theta A and another one over the space theta S, and I'll use this standard notation of pi for those priors. All right, so a little bit different situation here now. Let's look at what we call the common source problem, and this is trying to figure out whether or not the samples from the two different crime scenes can be attributed to the same wire coil, but we're not specifying what the coil is. We're not specifying it to be with a suspect because we don't have a suspect yet. Okay, so in this case, the evidence looks a little bit different because you're not going to have that population associated with the specific source. So you're still going to have that alternative source population, and that's defined the exact same way as the specific source. But now your other two sets of evidence are a little bit different because they both have unknown source. So that first unknown source set we'll call E sub U1, and that would be like the wire coils that came from one of the IEDs at one of the crime scenes, and then E sub U2 are going to be the copper wire that has come from the other IED at the other crime scene. Okay, and so our goal here is to figure out, did they come from the same source in the alternative source population? And that's what we denote as the prosecution hypothesis or the prosecution proposition. Or did you take two different sources from the alternative source population, and is that how the wire coils came to be, or the copper wires come to be? And that's what the defense says is going to happen. Okay, so really what we're trying to find here are two different ways that E sub U could have come about. So again, that E sub A is just you take your alternative source population, you sample a whole bunch of sources, N sub A of them, and then from each one of those N sub A sources, you take some samples. But now, did E sub U1 and E sub U2 come from M sub P for the prosecution or M sub D for the defense? Okay, so under M sub P, we say, well, you just sample one extra source from the alternative source population, and then you take some samples, and it's basically you partition them into E sub U1 and E sub U2, but they came from the same randomly selected or unknown source. But then under M sub D, we said, no, we take two different sources randomly from the alternate source population. So you have these two different unknown sources, and then from each one of those, you sample some set, and that's what you got for the copper wire from the two different crime scenes. Okay, so really the idea here is, did they come from one source or did they come from two independent but unknown sources? Okay, so our main goal here is to come up with some sort of value of evidence to say in each scenario, the common source or the specific source, which hypothesis should we be supporting by our evidence. So the way we do that is to do a Bayes factor. And so you can recall from part one that this is how we denote the Bayes factor. It's basically these integrated likelihoods of our evidence. Excuse me. But now we can write these in a little bit more detailed way based on our common source and specific source frameworks. So we can see that for the common source Bayes factor, in the numerator, we're going to pool those two sets of unknown source evidence together. But in the denominator, we can consider them separately because we're saying they come from two different sources. So that's what's going on for the common source Bayes factor. For the specific source Bayes factor, in the numerator, we take a look at the unknown source evidence, but assuming that it came from the specific source population, so that's why we're using this theta S here. And then in the denominator, we assume that E sub U has come from the alternative source population, so the parameter we're going to be using there is theta A. So these are the two different forms of the Bayes factor for these two different questions that could come about when you're trying to compute the value of evidence. So it's really important to distinguish which one you're actually addressing so that you can come up with the correct base factor for common source or specific source, because you can see they look very different. So we also talked about another way we could do the value of evidence is to think about the likelihood ratio. So in this case, we'll look at the likelihood ratio function, which is going to be a function of that unknown parameter value theta. So let's say we don't know what that looks like. So we look at just the likelihood of observing E sub u given m sub p in the numerator and then m sub d in the denominator. Okay, so the very similar thing here for the common source likelihood ratio. In the numerator, we pool E sub u1 and E sub u2 together because we're saying they come from the same source. But in the denominator, we need to consider them separately. And then a very similar thing for the specific source likelihood ratio. In the numerator, we assume the specific source population, so we use theta s. In the denominator, we use theta a because we assume it came from the alternative source population. So there's this third thing that we're going to consider, and we call this the true likelihood ratio. So that's if you were to actually know the values of the parameter that generated your actual evidence. Okay, so we denote this known or the true parameter value as theta naught, and we're just going to replace that for both the common source and specific source. And then this is basically just going to be 1 point of that likelihood ratio function that I just discussed on the last slide. And so what this theta naught is can take a couple of different interpretations depending on what paradigm you're using in statistics. I won't go into that too much, but just know that there could be a slightly different interpretation for what that theta naught is. But it's basically the same thing. Okay, so let's figure out how do these two things relate? How does the base factor relate to the likelihood ratio? Okay, so the base factor is just going to be one number for one given set of your evidence. And because you integrated over your parameter space, it contains in it all your measures of uncertainty. The true likelihood ratio has no uncertainty. You know the likelihoods, you know the parameter, there's nothing uncertain about it. This is really what we're trying to get at when we're trying to compute a value of evidence, is to a place where we know everything. And so the relationship that we found is that we can think of the base factor as being an integrated likelihood ratio with respect to this special posterior distribution. Okay, so for both the common source and specific source problems, you can get something like this, where that special posterior distribution is going to be the posterior distribution for your entire parameter vector, given your entire set of your evidence, so all three subsets, and you're going to assume that those have come as a result of the defense model. So you're going to assume M sub D in this special posterior distribution here. So one thing I'd like to note here is that if you don't know that true value of the parameter, you can't compute the likelihood ratio, the true likelihood ratio. So it's impossible really to obtain this true likelihood ratio in real life. And then as far as the base factor goes, this integral often does not exist in any closed form. So it's often really difficult to determine what this integral actually is. And we talked about in part one a couple of different ways that we might go about actually computing that. So if you're interested, go back to part one and take a look. But the real key point here is that these things are really hard to get in real life and often really impossible to obtain exactly. Okay, so if we can't get them exactly, then what should we do? And that's where we're going to talk about our different approximations. But one other thing that I think is an important relationship between the base factor and the likelihood ratio is that, here's just kind of this theorem. You don't have to know the details about it too much, but if you assume some sort of reasonable assumptions then you can find that as you collect more and more evidence in a case about the specific source population and about the alternative source population, your information about your unknown evidence, so E sub U, the traces, that's always going to remain fixed. But as you get more and more information about your specific source and your alternative source population, then the Bayes factor is going to converge to that value of the true likelihood ratio. And I think this is really important because there's a statistically rigorous argument then for using sort of these Bayes factors outside of a Bayesian paradigm, because they'll converge to a likelihood ratio, which you may use outside of the Bayesian paradigm, or kind of vice versa here. So there is a strong statistical argument for using Bayes factors in this case. So like I said, if we can't actually figure out what this Bayes factor is, well, what else can we use? And so a lot of the goal of my dissertation essentially was to find some approximations of the value of evidence that would result in an approximately admissible decision rule. Excuse me. Okay, so that basically means that we can find a substitute for the Bayes factor that we could plug into this equation to update our prior odds and get our posterior odds that's going to be pretty close in probability. Okay, so we're going to look at two approximations for my dissertation, one that I call the Bernstein-von Mises and one that I call the Neyman-Pearson approximation. And we're going to talk about how these are in fact going to be things that we can plug into that V tilde and get an approximately admissible decision rule. Okay, so basically for this slide, the Bernstein-von Mises approximation is, there's this Bernstein-von Mises theorem that says that if you get more and more relevant data, then eventually your posterior distribution is going to converge to a normal with a particular mean and covariance. Okay, so basically what that is that the mean is going to be the MLE for your parameter, in this case, under the defense model, using the entire set of data that you have. In this case, our evidence, so all three subsets. And then that covariance is going to be the inverse of the observed Fisher's information matrix. Again, you assume that the defense model is true in this case. So really what we're doing is we're taking the Bayes factor and just replacing the posterior distribution with a normal. Okay, so this is kind of nice because we know that the Bayes factor is really sensitive to the choice of prior distribution that we choose. Okay, so this is just basically replacing that prior distribution that you would have to choose with one distribution that's pretty well known to everybody, the normal distribution. So it takes a little bit of the guesswork out of what you need to be doing to compute the value of evidence. So for the specific source, this is basically what it looks like. And then a similar thing for the common source. Really all you're doing is you're integrating your likelihood ratio function now with respect to a normal distribution instead of that special posterior distribution. Okay, so this sounds like a really easy thing to do. You just replace it with a normal, but you need to be able to compute the maximum likelihood estimates, and even more troublesome, because maximum likelihood estimates are easier, you need to figure out what this inverse observed Fisher's information matrix is. And depending on kind of the dimensionality of your data and things like that, these things can kind of be a pain in the butt to compute. So that's one downside of the Bernstein-von Mises approximation. But one of the good sides, I think, is that it has this statistically rigorous foundation to it, in that if, again, you observe more and more evidence from your specific source population and your alternative source population, then this thing, the difference between the Bernstein-von Mises and the Bayes factor is going to converge to zero. So you're really shooting for the right target here. You're not going to be diverging off to something that you're not interested in computing. And really there's just kind of the few standard assumptions that held for the last theorem that you need in order for this result to be true. Okay, so that's our first approximation. Our second approximation here is what I call the Neyman-Pearson approximation. And I call it that because it's kind of a generalization of the Neyman-Pearson test statistic that we would use in the frequentist setting. And so the idea here is to figure out what those values for your parameter would be under both the numerator and the denominator, but we're going to be doing that sort of separately. So we're going to be optimizing those likelihood functions separately. Okay, so really all we're trying to do here is to find a bunch of different MOEs. So for the specific source, oh, excuse me. For the specific source Neyman-Pearson approximation, we need 4 different MOEs. So in the numerator, you can see that we have 2 of them. The one that's the theta s hat star, that one is going to be where you find this MOE by pooling E sub s and E sub u together, because that's what the prosecution model says that we should do. Okay, so that theta s hat star, that's going to be found by pooling E sub u and E sub s together, and then we just leave E sub a by itself to calculate the regular MOE theta a hat. Now, in the denominator, we want to do something different by pooling E sub u with E sub a, because that's what the defense proposition says we should be doing. So that's where the theta a hat star comes in. We pool those together to find that MOE, and in this case, theta s hat is just the standard MOE for the specific source alone. We do a very similar thing for the common source. So to find the MOE in the numerator, we pool E sub u1 and E sub u2 together and treat them as if they have come from one source. And in the denominator, we consider them separately as if they have come from 2 different independent sources from the alternative source population. And that's where those 2 different MOEs come in for the common source Neyman-Pearson. Again, we have this really nice statistical result for the Neyman-Pearson approximation. If you assume some sort of nice things happen, we'll eventually get that the Neyman-Pearson approximation does in fact converge to the true likelihood ratio. So this, I think, has a big benefit over the Bernstein-von Mises, is that it's way easier to get just these MOEs than it is to do all that business with the Fisher's information matrices, because a lot of our standard statistical software, with just a couple of tweaks, will give us the MOEs that we need. On the downside, that would be assuming that we have the form of the MOE for most of the standard distributions that we work with. If you, however, have a likelihood that is not sort of a standard distribution, then you need a little bit more sophisticated optimization techniques to find those MOEs. But there's a lot of literature on how you might do something like that. So that's kind of the good news with that one. So kind of the overall result of my dissertation here is that if we have some sort of nice and easy assumptions hold, then we can find an approximate value of evidence that means that we aren't going to be that far off if we use this in an actual case. Like I said, there are kind of some downsides to each one of these. These are by no means perfect, especially in terms of practicality. And so I think a little bit more work is going to need to be done with these to figure out, well, how big do my sample sizes for E sub s and E sub a need to be so that I can use these confidently in court? So I think that's one thing we need to look at, are some sort of sample size calculations here and figure out whether or not this is going to be realistic in practice. So that's our next steps with the Neyman-Pearson approximation. Okay, so I've sort of very briefly run through these recent developments that have come out of my dissertation that I think have been good developments for us towards just at the source level value of evidence. quantification problems. So I'd like to take the last few minutes here of the webinar to talk about some controversies that have come about as we've been developing these different value of evidence quantification methods, and talk about some of the things that that I think need to be addressed before we can actually talk about using these things in court. So one of the things that has been a really big topic lately regarding value of evidence is whether or not you should give in court, along with the value of your likelihood ratio or Bayes factor, some sort of uncertainty quantification, maybe something like a confidence or a credible interval associated with that single value, to basically give the idea that these things are not exact, that there is a little bit of wiggle room. So that's some of the that's the first thing that we're going to talk about, since that's some of the big debates that are happening currently with these value of evidence research programs. And then the last thing we're going to talk about is some controversies that have come about as a result of the PCAST report, and the commentary that's come along with those. So we'll just briefly touch on a couple of these things before we end today. So in the debates about whether or not we should quantify uncertainty, there are three papers that have sort of stuck out in my mind as being the first ones that I was aware of that I read that talked about whether or not we should do this. Should we quantify uncertainty regarding likelihood ratios and Bayes factors, or should we not? Okay, so this started out in law, probability, and risk. And there's this one original paper, like I said, that I'm aware of that led to these two different commentaries or responses to that paper. And I think they have sort of really cool names too, so that's why I put them up there. The dismissal of the illusion of uncertainty in the assessment of an LR, and uncertainty in LR to integrate or not to integrate, that's the question. So they have these really cool catchy names. So let's just kind of briefly talk about what I think were the highlights of these two papers. Now, I want to make sure that everybody knows that these are just my interpretations of the important points of these two papers, and that I in no way discussed these with the authors, and so if I misrepresent anybody's position, I beg forgiveness. Okay, so for this first one, the idea with this one is saying that from a Bayesian perspective, we need to think more carefully about whether or not we should include uncertainty quantifications with a Bayes factor. So really, I took some of these main points from this article because I think they're important. The first one that they talk about is that probabilities are not states of nature, but states of mind. And so this means that in the natural world, the likelihood ratio doesn't exist. That's not something that exists in the real world. That's something that only exists in a person's mind, because it's a ratio of probabilities, and probabilities are specific to a single person. And so the authors of this paper argue that it doesn't make sense to estimate something that's a state of mind. It only makes sense to estimate something that's a state of nature, because it needs to exist in the real world and have this sort of implied true quantity to it in order to estimate it. So the other point that they make here is that probabilities need to be given by a single number. So if you think about this from a Bayesian perspective, if you give two different numbers for a single probability of one event, then that's not logical, because you're giving two different probabilities to the same thing happening. So it's not logical to have two different numbers. It must be a single number. And so really, I think you can kind of combine these first 3 points to say that if, in fact, probability is basically this quantification of how you personally are uncertain about something, then it doesn't make any sense to add an additional level of uncertainty to uncertainty. That just is going to muddy up the water. So basically what they distill from these points that they make is that for a particular case, the forensic science should give to the court just one single number, which is the Bayes factor, and not give a range of values, because that would be adding an additional level of uncertainty to your uncertainty already. Okay, so for this particular thing, they say don't do anything like an interval quantification to go along with your Bayes factor. So the first commentary paper was by a group out of the NFI, and they look at things from a little bit different perspective. So they say that, sure, if you choose to do this from a Bayesian perspective, like they talked about in the previous paper, then they don't have any disagreement with this. They say that, of course, it does not make any sense to add an additional level of uncertainty to your uncertainty. But they say you could choose a different path. You could choose not to look at this from a Bayesian perspective. So you could choose to look at this from the perspective of approximating the likelihood ratio instead of the Bayes factor. And so what you could do is you could look at the data that's available to you and come up with some sort of estimate of your parameters and then plug that into the likelihood ratio. Okay, so sort of in an analogous way to what I talked about as being the Neyman-Pearson likelihood ratio, although they talk about it in a slightly different form. But they say in that case, you're actually estimating a parameter, and so it makes complete and total sense to talk about the uncertainty with regards to that parameter, maybe in the form of a credible interval if you choose to estimate that in a Bayesian way. And so they basically said that outside of the fully Bayesian approach, it does make sense to talk about estimating the likelihood ratios. That's something that is fully supported by statistics as long as you're not being a Bayesian. So their final conclusion of this paper is that yes, you should in fact be giving an interval quantification with your value of evidence, because they believe it's more informative to the courts to give this. And that if you are including all of your uncertainty into one single number, that you are depriving the courts of some information that would be useful to them. Okay, so they argue that you should go about this in a different way, approximate a likelihood ratio instead, and in fact give, excuse me, an interval associated with your uncertainty in that likelihood ratio. And then I think kind of an often overlooked paper that goes along with this commentary was one that came from more of a practitioner's point of view, which I think made some very good points in that there is kind of a gap between the sophistication of the methods that statisticians propose to use as being the best methods and the statistical knowledge of the forensic practitioners who should be using them. Another point that they bring up is that in the real world, in a lot of cases, that somebody, a practitioner who works at a lab, is not giving a conclusion based only on their knowledge, that needs to then be examined by somebody else in the lab, and then that conclusion comes from the entire lab. So they say that this idea of subjective probability doesn't really make any sense in this case, because the conclusion is not representative of one single person who's making these probability assessments, but in fact a collection of individuals who all represent a lab, for example. And so really the idea here that I took away from this is, don't lose fans of your methods because you're bickering amongst yourselves and then using that bickering to criticize the people who are using your methods. So don't lose your fans. And I think that's an important take-home message, is we need to be aware of who's using these methods. So they say, well, maybe it's a good idea to admit in the beginning that we're going to do something like give a range of likelihood ratios, even though we know it's not correct, but we think that this is a step forward from using maybe some vague verbal expression like, you know, some of the things like, well, I know it was this person because I've been doing this for 30 years and that's what my experience tells me, something along those lines. And so that is I think the perspective of the author of this commentary is we got to take baby steps so we don't lose our fans. And while I don't necessarily fully agree with any of these with any one author fully of these 3 different papers, I believe that there are some very good points that each of them make. And then I think this is really kind of what sparked the second round of debates that have come about in Science and Justice. So this was a virtual special issue on this idea of whether or not we should be quantifying uncertainty. And so it gained quite a bit of traction. There were 7 position papers, 3 response papers, and 3 reply papers that everybody has made some very good points in this, I believe. And so if you want to know specifically what my position was at the time, I was one of the authors in collaboration with Chris and Cedric on one of those position papers. And I would like to talk about all of these in more detail, but kind of as a time constraint here, I won't get a chance to do that. But if you're interested in what a lot of these people have to say, I've cited all of these, and they will be available in the references, so you can go ahead and take a look at that. And then kind of as the climax of this debate, there was this press release that came out in 2007 that said, NIST experts urged caution in use of courtroom evidence presentation method. Use of the likelihood ratio is not consistently supported by scientific reasoning. And so this was a press release in response to a paper by a couple of NIST researchers that came out, and it got a lot of controversy as a result of this paper, and there were 4 responses that I know of to this paper. And I really think it fits along into this idea of whether or not we should quantify uncertainty. And so what the 2 NIST authors have said is, well, there's been a lot of talk about Bayes factors and likelihood ratios. Let's take a step back and figure out, well, should we even be using them for court? Are they set out to do what we actually ask them to do? And so they find that this paradigm that everybody says we should be using is not in fact supported by arguments of Bayesian decision theory because of the way we say we should go about this. So there's kind of a clash between the decision maker, who is supposed to be coming up with priors and things like that, and then the likelihood ratio, who is made by not the decision maker, but by the expert in the case. And so they say that this is not something that should be done in Bayesian decision theory, where it's supposed to be the subjective opinions of just one single person. And so they say that, well, maybe you shouldn't do this for just a single person making a decision. It can be a very valuable tool to communicate to the decision maker or the trier of fact maybe what's going on, but maybe it shouldn't just be one thing that we use in the only thing, but maybe it could be one amongst many different methods that we can use here. So that's sort of the opinion of the authors, and they come up with this idea of this lattice of assumptions and uncertainty pyramid as a way of organizing what you have looked at into different modeling assumptions and things like that, so that if your modeling assumptions change, you can show how your values of evidence might change, and that would give us an idea of how uncertain you might be in any particular case that you're looking at when you're making a likelihood ratio. And so this, like I said, sparked a lot of controversy. I'll just talk sort of briefly about a couple of the responses that came out. So one of the responses say that they're missing the point here. This practice doesn't actually exist and no one advocates it, so why are we arguing against it? There was another comment that came out and said, okay, you have an issue with maybe how to use these in court. Here's a suggestion for how you might do this differently. And then another one gives a basic argument that came from I.J. Good many, many years ago that says if you want to have an admissible decision rule when you are presenting evidence in court in a Bayesian setting, then the only way to do that is to give a Bayes factor. So they're saying that's the reason why it's the only way to go about this, because it's the only admissible form. And then there's another comment that said, well, we really need to be careful about sort of sensationalist press releases like NIST gave out, because it could impede progress towards actually analyzing forensic evidence in courts, they say in the US and across the world. So really there's been a lot of argument about this amongst ourselves about what should we do when we are presenting evidence in court. Should we give uncertainty quantifications or should we not? And how do we go about doing that? And this is something that's been discussed, I think, for quite a number of years, and an important thing that we should be discussing. So I think one of the good things that came out of these controversies in each one of these, like I call them the different rounds, is that it got a lot of people talking and trying to reaffirm and back up their opinions and their positions. And I think that we're making headway, and we need to consider a lot of different things when we are considering whether or not we should quantify uncertainty. So just as the last comment here, I said we talk about the PCAST controversy. And so a lot of people read the PCAST report, which we talked about a little bit in part one, as being a report which advocated the use of the two-stage approach. So the two-stage approach is something, again, that I sort of briefly introduced in part one. So if you want to go back and take a look at that, if you don't know what the two-stage approach is, please feel free to do that. And really what happened with these two responses that I know of to this PCAST report is they say, I don't think we should be looking at the two-stage approach. We really should be going towards this idea of the Bayesian paradigm or the likelihood ratio framework. And so that's what these two different comments are saying, is that we need to think about which evidence interpretation paradigm we should be using, and which one should we be advocating for use in the US and other courts. So really what I want to get through today is that there's been a lot of progress towards finding better ways of computing the value of evidence. And as we've been going through and making all this progress as a community, it's sparked a lot of controversy because researchers have sort of been moving in these opposing directions as to which paradigm of evidence interpretation they want to move towards. And so I think because of this sort of splitting, there's a lot of work that still needs to be done, and we need to kind of reconcile a lot of these arguments, I think, before anybody is going to trust us to use any of these things in practice. So thank you for joining me for part two. I appreciate getting the chance to be heard by you guys. Again, I listed like 40 some references, so way too many to put on this slide. So you can email me with any questions. The references, I believe, will be put up with the slides on the CSAFE website. So at this time, I'd like to take any questions that you guys have. Any questions?
Can you read that from where you're at?
Is it the whole message?
Yeah, can I scroll up on this?
Yeah.
Or okay.
You just drag that box over.
Okay, from Jeff Salyards, he says, from a practical point of view, I'm not sure the distinction of the two initial scenarios makes a real difference. It seems that a forensic examiner is presented with two samples of copper wire in both scenarios. Then we are asked, do these match, share a common source, etc. Whether or not the second wire was found in the suspect's garage or in another IED doesn't seem to affect the analytical results or LRs. It may affect the prior probability. Okay, so Jeff, I agree with you that this would not affect the analytical results. The analytical results are essentially going to be the same. Where the wire was found is not going to make any difference as to its chemical makeup. Okay, and so where I disagree with you here is that I do think it makes an effect on the likelihood ratio because of that statistical framework that I put up, where in one case the source of the wire is fixed, and in the other case we consider it to be random. And so,
Click on your slide.
oh, that's why. Okay, click on my slide. Okay, and so let me go back here and hopefully I can show you the two different forms of the likelihood ratio. And so in this case, it really is going to make a difference because of these two different likelihood ratio forms that I'm showing you here on this slide. So they are going to be two different values. So the value that you would get for the common source likelihood ratio is going to be different than the value you will get for the specific source likelihood ratio. So in that case, it does make a difference. Those values are going to be different. And this is something I'm happy to talk to you more about this. And so, yeah, I will very happily talk to you about this offline and give you an idea of how I derived these equations, and hopefully give a little bit more detail on that, since I kind of just went at an overview level in this talk. So. Did I update my view on the use of interval quantifications? No, I did not. I just wanted to give an idea to everyone about what the different views are. But my view has remained the same as the position paper that I published in that Science and Justice special issue. So Hal Stern says, London Ire seem to focus on uncertainty due to model choices rather than uncertainty about parameters within that model. Can you comment on this? I would agree with you, Hal, that is definitely what they seem to be focusing on with the, I think they call it their lattice of assumptions, or the uncertainty pyramid. And so I think that there are multiple levels of where uncertainty could creep into the quantification of the value of evidence. And so we need to have, in my opinion, different discussions about what we should do with different types of uncertainty, because I think they should be handled differently. And that's one of the points that I make in that Science and Justice paper, or I try to make anyway. Any other questions? any announcements that I need to make?
No.
Okay, I'll wait just a little bit more in case we have any more lingering questions, but otherwise, thank you all for joining me today. Feel free to let me know via email if you have any other questions. I'd be happy to discuss any of this over email or phone call or anything like that. So it does not seem like there are any more questions. So thank you all again for joining me. And I look forward to hearing from anybody via email.